So good afternoon, everyone. So thank you for your time and welcome to my talk. Today is my pleasure to share with you my research, which is miniature soft robots, road to minimally invasive surgeries. The outline for today's talk is shown over here, right? So as an introduction, what are miniature robots? Basically, they are mobile devices that are really, really small. So how small are we talking about? Basically, all the dimensions of the robot should range between 10 microns to a centimeter. As an example, you can see that we have a star-shaped robot that is in microscale, manipulating some microscale screws. A very unique characteristic about this class of robots is that they can utilize their size and mobility to non-invasively access highly confined and enclosed spaces to perform a wide range of micro-nano manipulation tasks. Due to this ability, scientists envision that this technology could one day revolutionize minimally invasive surgeries. The dream is that one day we can inject all these robots into our body, navigate them to a targeted location in a non-invasive way, and perform treatments. The potential impact of this technology is very significant because if we compare it to the state-of-the-art technologies that use tethered catheters to perform minimally invasive surgeries, the small-scale technology has two distinct critical advantages. Number one, due to the size of the robot and its mobility, the treatments that it can give will be much less invasive. So what does it mean? It means that the patients will experience less pain and they can also recover faster. The entire procedure will also become safer because you reduce the risk of infection and also mechanical trauma. Point number two, once again, because of the size of the robots and the mobility, they can actually access places that those tethered catheters could not reach, which is why having higher accessibility enables them to be able to create and enable unprecedented new treatments in the future. So heading towards this goal and dream, many miniature robots have been created in the last decade. In general, we can classify them into two categories, the rigid ones and also the soft ones. After working on this research for many years, I conclude that the rigid ones could only achieve simple rigid body motions and nothing else, which is why I started to look more at the soft robots. I realized that not only can they move, they can also generate a series of time-varying shapes that can enable other functionalities. So for example, the robot over here is actually a mobile gripper. It can not only move, but it has two arm-like structures that behave like chopsticks. So what it can do is that it can move towards a micro object, use its chopsticks to hold the object and transport it and place it at a desired location. This type of functionality could only be achieved if you are using this kind of soft robots, which is why in this talk, we'll be focusing on this class of robots. Looking into the literature, there already exists many different ways to actuate and control such soft miniature robots. For example, you can use heat, chemicals, electricity, pressure, light, and magnetic fields. After studying all these different modes of actuation, I conclude that remote magnetic actuation has the highest potential to translate this technology for biomedical purposes. This is because magnetic actuation has three distinct advantages over other actuation methods. Number one, unlike actuation methods that use like heat, light, and pressure, magnetic fields can be specified not only in the magnitude, but also in their directions and spatial gradients. So what it means is that by having more parameters to control our robot, it means that the robot has higher potential to create more complex functionalities. Point number two, magnetic fields can easily and harmlessly penetrate through most materials, including our human body, which is why this technology, or rather this actuation method, is very compatible if you want to use such robots for surgical purposes. point number 3. Unlike other soft miniature robots that require minutes or even hours to create a shape change, magnetic soft miniature robots could create a series of time-varying shapes within a fraction of a second. And such fast response is very ideal and beneficial if you want to use them for medical purposes. So to introduce the working principle of how magnetic soft miniature robots work, I'm going to use a beam over here as an example. For the beam to actually respond to magnetic fields, we must first embed small little magnets into the robot, whereby all these small little arrows represents a small magnet. The collection of all these magnets is also known as the magnetization profile of the robot. Once the profile has been programmed into the robot and we expose the robot to external magnetic fields, the interaction between the field and the profile will deform the robot, allowing it to change a shape. If we change the magnetic field across time, we can therefore generate a series of time-varying shapes. So to highlight and to demonstrate the potential of this technology, this is a Taylor swimmer that we have created based on this technology. What it can do is that, hold on for a while, it's not playing. So let's see. We can see actually what this swimmer can do is that we can actually create a traveling wave down its body to enable a swimming locomotion. Using such a swimming locomotion, we can command the robot to follow a trajectory. For example, in this case, we allow it to swim a CMU path. The creation of such a swimmer, right, is highly significant because since 1951, after Taylor has proposed such a swimming locomotion, many people have tried to create this in real life. After half a century, this was not possible until in 2014, whereby we use magnetic actuation for soft miniature robots. Then were we able to create such a complex swimmer, right? Despite the potential of this technology, I need to highlight that there was a very big critical limitation in this technology, and that is people could only use their human intuition to guess what is the required magnetization profile and magnetic fields such that they can create the desired time-varying shapes to achieve a certain functionalities. And this is a very big obstacle if we really want to develop such a technology and translate it for biomedical purposes. And one of the big challenge, like why they cannot develop a very systematic way to design and control such robots, is because we don't really understand the physics behind it. So, as a result, in view of all these challenges, I'm going to propose a universal design method. The objective of this method is that if I'm given a series of time-varying shapes, we can use our method over here to allow computers to automatically generate the required magnetization profile, M, and also the required magnetic fields, B, to control the robots. All right? So there are 4 steps in this universal method, and I'm going to use a simple beam to illustrate all these 4 steps. So we start with step number 1. We are going to first define the desired kinematics. That means what kind of time-varying shapes that we want. We can do so by first defining a parameter we call theta, which represents the rotational deflection of the beam at any point of space, S, and also at any time of time, T. Okay, once we define theta, we will perform a quasi-static analysis on the beam. To make the analysis generic, we will pick an arbitrary time instant T, and we will also pick an arbitrary infinitesimal small element, and we will look at all the forces and torques acting on this element. The forces and torques acting on the element at the ends represents the internal forces and torques, while the forces and torque acting on the center represents the magnetic torque and forces respectively. Once we have drawn all these forces and torques, we will perform a force balance analysis in the x and y axis for this element. We get the expressions shown over here. Next, we are going to use the Euler-Brillouin equation, whereby we relate the bending moment mb with how the robot is going to deform. Finally, we're going to perform a torque balance equation for this element, and we are going to substitute all these three expressions into that equation. What we finally get is a governing equation, the physics that really describe how this technology can work, especially for this beam. There is actually a physical meaning behind this governing equation. The left-hand side of the equation actually represents the desired kinematics that we want the robot to do. That means the desired time-varying shapes that we want the robot to create. This is something that we specified. The equation on the right actually represents what is the required magnetic torque and forces that we need to program such that we can actually balance both sides of the equation. I highlight that if we are able to balance both sides of the equation, it means that we are able to design and control the robot to achieve its desired functionalities. So this is step number one. Next, you will use this governing equation that I rewrite over here, and we'll move to step number two. Before we do so, I would just like to show you the explicit representation of how the magnetic torques and forces relate to the magnetization profile M and also the magnetic fields B. Unlike other traditional methods that we use human intuition to guess what are M and B, over here we are going to use Fourier series to represent M and B first. The difference between these two Fourier series is that we assume that M, which is the magnetization profile, could only be a function of displacement or space, S, but not time. The reason we do so is because we assume that once the magnet has been magnetized and deployed, we cannot remagnetize it again. On the other hand, B can change across time. That means magnetic field can change across time. But we cannot change in space because the size of the robot is too small for us to do that. So these are practical constraints that we will consider when we are trying to design and control them. Nonetheless, despite these constraints, a very big significant advantage of using such a representation is that the Fourier series representation includes and encompasses all possible solutions. That is why, if our time-varying shapes that we specify is feasible, we can always substitute such a representation back into the governing equation and balance both sides of the equation by finding the optimum Fourier series coefficients A, B, alpha, and beta. So we will need to go to the next step to show how we do this. We have many unknowns, right? A, B, alpha, betas, but we have only one equation. So how do we really solve them? To do so, we need to create new equations. Creating a new equation can be achieved if we sub different values of S and T into the governing equation. So for example, when T is equals to T1, we discretize the length of the beam from S is equals to S1, S equals to S2, all the way until S equals to SL. And we're going to sub all these different values of S with T equals to T1 into the governing equation. We can actually generate L number of equations just for time instant T equals to T1. If we continue to do this from T equals to T1, T equals to T2, all the way until T equals to TF, we can therefore generate L times F number of equations. So we can create more equations so that we can solve all these unknowns. So all the equations on the left can be represented by a simple vector that we call MB. And everything on the right can be represented by a matrix K multiplied by U, whereby U is a vector that comprises and includes all the information of the Fourier series coefficients that we want to solve. So using this format, we'll go to step number 4, whereby we formulate an optimization problem. The objective and aim of this optimization problem is that we are trying to minimize the differences between the left and right-hand side of the equations by finding the optimum Fourier series coefficients. We also make some constraints because of practical reasons. We say that what is the maximum amount of magnetic field we can supply to control our robot. So once we specify this optimization problem, we allow computers to automatically generate the required Fourier series coefficients. And this will in turn give us the required M, which is the magnetization profile, to design our robots, and also B, the required magnetic fields to control them, right? So using this method, we have synthesized and create multiple miniature soft robots. But because of time constraint, I'm just going to show two examples over here. The first device that I'm going to show you is called the artificial cilium. A cilium, or rather a biological cilium, is actually a hair-like structure that can be found on a microorganism. What it can do is that it can generate a very complex beating pattern that can be divided into two strokes, the recovery strokes and the power strokes. Due to this amazing beating pattern, many scientists and engineers have tried to create a cilium device, an artificial cilium device that can create such beating patterns. But this was really challenging, and even after many decades, people have achieved very little success. Nonetheless, using our method, we can automatically ask the computers to generate the required magnetization profile for the robot, and also what are the required magnetic fields to actuate them. And this is based on all these parameters, we were able to design, construct, and test on such devices. Before I show you the videos, I just want to highlight that you can see the profile and the magnetic fields are highly complex. This is something that you cannot really use human intuition to really guess it, right? This is not simple, okay? But anyhow, based on all these parameters, this is what we have. First, I'm going to show you what is the beating pattern of a biological cilium, all right? In a very simple animation. So first, this is the power stroke, and then the recovery stroke. This is what we can achieve, what we can build and control. Power stroke and recovery stroke. Power stroke and recovery stroke. While this device still could not exactly 100% mimic how a biological cilium behave, but I want to highlight this. To my best knowledge, this is already the best artificial cilium that has been created to date. All right? The second example is that we have built a soft robot, a miniature soft robot that can actually create 7 different types of locomotion. To enable all modes of locomotion, we want the robot to be able to create 4 principal shapes, as shown over here. And they can be divided into 2 categories, the small deflection ones and the large deflection ones. At the small deflection ones, we want the robot to create a sine shape and a cosine shape. And because the deflections are small here, we can actually superimpose these 2 shapes if necessary. This is something very beneficial if you want to create a swimming locomotion like the Taylor swimming sheet. On the other hand, when we want the robot to create large deflections, we want it to be able to create a C and a V shape, all right? And under such a configuration, we can actually control the rotational displacement or the angular displacement of the robot. So using all these 4 shapes, we can enable 7 locomotions. This is the video. On land, it can roll because rolling is the fastest way to transverse across a solid terrain. On the water surface, it can perform the Taylor swimming sheet locomotion. The video is slow now because I slow it down by 9 times for you to see them, all right? The same robot can not only swim on the water surface, it can also immerse itself into the water bath. Under the water, inside the water, it can create another swimming locomotion that allows it to swim up again. We call this swimming locomotion a jellyfish-like swimming pattern. And once it's on top, it can actually reach the water surface, all right? The video is slow because just now was slowed down by 80 times. Now it's like slowing by 17 times, all right? The same robot could also climb a meniscus. It can do so by deforming itself into a C shape to enhance its buoyancy. Once it's at the interface of land and water, we can use like the rolling locomotion to allow it to land on solid terrain. On land, we can use another locomotion if we want to precisely locate its position. This is a locomotion that we call walking. But if walking is not possible because it's been blocked by a big obstacle, we can change the walking locomotion into a jumping one. Yeah. Yep. Yeah. No, it's on land. The whole thing is on land. Yeah. So after we jump across, we can resume our walking locomotion, right? So once again, I highlight rolling is the fastest way to traverse across solid terrains. Walking is a more precise way to locate them and position them, all right? There's some jerking because our experimental setup is supposed to be only in the workspace of this, but this can be solved, all right? That's an engineering issue, all right? So like what I say, walking is a good way to precisely position the robot, but what if it's blocked by a narrow tunnel? We can change the walking locomotion into a crawling one. And once it's out, we can resume the walking locomotion because it's a very precise way to position our robot, all right? So, in summary, in this talk, I've shared with you a universal design method for magnetic miniature soft robots. I believe that this method have allowed us to fully capitalize the full potential of this technology, which is why I also believe that this is a significant step towards really translating this technology for future biomedical applications, especially if we are looking at minimally invasive surgeries. So to demonstrate, while we are still far away from really realizing those applications that I mentioned, but we can actually see the potential of this technology through these two showcases that I've shown, especially like the artificial cilium is really something that people have tried for really many, many decades, but they have achieved really little success, all right? And also a soft robot that has 7 different types of locomotion. So before I end my talk, I just like to thank the people who I've worked with for many, many years. My advisors, Professor Martin City from Max Planck Institute, and Professor Yeo Sung Huat from Nanyang Technological University. I just want to especially thank them. And the rest of the people here, I've worked closely with them for many years, and they are also my very good friends. So thank you for your very kind attention. I'm just going to show you the video again so that you might be interested to know. And I'll be glad to answer any questions. Thank you.